Okay, next mode of partition chromatography is what we call reversed or reverse. Some people leave that D off. Reversed phase liquid chromatography, or RPLC. As I mentioned before, a lot of folks just think of this as synonymous with HPLC because it's the most common mode of HPLC. Here's our stationary phase particle. Here's that dangling siloxane, so there's actually an oxygen there. And this thing has some R prime groups. And it has the main feature here, the R group. And in reverse phase liquid chromatography, the R groups are, relatively speaking, non-polar. This is like taking the organic phase of a liquid-liquid extraction and immobilizing that as the stationary phase. And the chemistry here is mostly really straightforward. So usually we talk about these columns in terms of the number of carbons dangling off of them. So really common R groups here would be these, let's see here. Well, yeah, I guess that's, I'm trying to think of it. There's the particle 1, 2, 3, 4. There we go. 4 carbons. It would be really common to call this a C4 column. A C4 column, these are saturated hydrocarbons. That's basically butane hanging off the edge of a particle. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. This is a C8 stationary phase. Sometimes it's called octal, an octal stationary phase. Here comes the fun one. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. C18, super common. This is octadecal or decile, an octadecyl column. It's not all just these saturated hydrocarbons. Sometimes you want to get some pi-like characters. So these phenyl columns are not uncommon. That's a phenyl functional group that would be hanging off of this chlorosilane here, or the silane here, that would turn into our stationary phase. So that's composition of the stationary phase. Let's talk about strength of the mobile phase. We'll do this again by considering gradient elution in RPLC. When we do that, we think about a change in mobile phase strength over time. We generally talk about that in terms of percent solvent B. Make sure that looks like a B for you guys. And a little bit harder to put a term on this, but for reverse phase liquid chromatography, what we're really talking about is non-polarity. Right? So as time goes on, this thing gets stronger by becoming less polar, right? Becoming more non-polar. In other words, that is high polarity and that is low polarity. And just like with normal phase, this makes sense, right? If we have these basically butane, octane, or octadecane solvents that are varying degrees of nonpolar dangling off here, and we're kind of competing for solvation there between the stationary phase and the mobile phase, then as we get less polar in the mobile phase, we will compete better for that solvation, right? It'll become a stronger mobile phase and things will come off faster. We have the exact same considerations. We basically, for all the modes we've talked about, we have the same mobile phase considerations. We need to think about miscibility of A and B. Miscibility. We need to think about detector compatibility. And for those reasons, here are the real kind of standards for doing this kind of work. So your standard A, that's basically here. That's what you're predominantly pumping when you're at a low percent B, right? You're essentially at 0% B, you're at 100% A. And the standard here would be an aqueous solvent of some sort, typically just straight up high purity water. I'll say it's often buffered so that we have good control over pH. Right, so it's often buffered. And then the classic B solvent would be acetonitrile. And acetonitrile is often in the literature and by me abbreviated ACN. So acetonitrile, for the record, that's CH3 with somebody chirp in with a comment. The CN, it's highly poisonous. It's late at night here, guys. I'm recording this at 11:30 p.m. right now, so my brain is is mush. I don't know why that's not cyano. No, yes, something like that. I don't know. Whatever. Sorry, everybody. So another one here would be methanol, MEOH, methanol. And hopefully we can all imagine the structure of methanol. I don't have to embarrass myself again by trying to remember what a C triple bond N is called at 11:30 at night. Okay, so stationary phase composition, mobile phase strength. Let's talk about retention order. And retention order in reverse phase LC is where the term reversed comes from. So retention order in reversed phase liquid chromatography is the opposite of normal phase. It's also the opposite of adsorption chromatography, right? Because normal phase is the same as adsorption. In other words, we are going to elute the most polar things first, and the least polar things will be retained longer. Or these have low retention factors and these have high retention factors. And it's this opposite that gives it the name reversed. Okay, so it turns out we talked before about, so if here's our silane, right? And we talked before about these, what I'm going to call now residual hydroxyls. And it turns out these are, so let's call these residual silanols, right? SiOHs. They're a bigger deal here. And the reason they're a bigger deal is because they're working in exact opposition to how our nonpolar solvent would work. So in other words, if we're trying to let polar things pass this R group and retain nonpolar things, but here's something that wants to hold on to a polar thing. Whereas in normal phase, these things are making the stationary phase stronger. That's absolutely true, and that can be bad. That's what's giving our, some peak asymmetry and some high retention factors. But at least they're working in the same mode, right? At least they're trying to hold on to polar things, and so is the stationary phase. Here we're getting this total opposite competition, and it can be a big deal. So there's two strategies, and I want to be clear that these two strategies, they're not really unique to reverse phase. I mean, people absolutely do this when they're designing normal phase columns, but because residual silanols are a bigger deal here, we're going to talk about them here in the context of reverse phase. Two strategies for handling these, making sure they're not a problem. So the first strategy is called end capping. And the idea here is to in the fabrication of these columns, right? So this isn't during your chromatography experiment, but in the fabrication of these columns, we're going to functionalize the residual OHs. So after you've done your full addition of what your C8 or your C18 or whatever, with a chlorosilane. So here's our chloro. Here's our silicon. Trimethyl, right? So this is just meant to imply CH3, 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 right? Trimethylchlorosilane. Let's give it that name. Trimethylchlorosilane. And the reason this works is because if you have, say you have a big C18 here, there's like some steric hindrance to getting as many of those packed together as possible. Because although we picture it as a string that kind of sticks out this way, it's actually a piece of spaghetti. It flops around and it's going to block things from getting in close. But because this trimethyl, these CH3s, this is basically the smallest chlorosilane you can produce, it can actually find its way down here to the surface and you can get that same substitution reaction we saw previously, but it can work on the leftover hydroxyls that the C18 never could have gotten to. So that's the concept of end capping. There's a second way to do this, and this is the reason why we've been calling these R prime. So the second way to do this, I'm going to try and squeeze this in here just because I'm too lazy to grab a new piece of paper. So here's one. Come over here for two. And the concept is to use bulky side groups. So by the side groups, I specifically mean the R primes. Right, if we add big bulky side groups here, we can leave these underivatized OHs as they are, but the big bulky side groups will prevent the analytes from getting down in there and suffering some of this non-specific adsorption with the residual silanols. So a couple of big bulky side groups that are common for this kind of work would be something like isopropyl groups, isopropyl or tert-butyl side chains, and those are going to take up so much room over here on the side. They are going to prevent analytes, really sterically prevent analytes from interacting with the surface of those particles. Okay. Let's keep talking about reverse phase. It's worth it because it's such a common methodology. How common? So reverse phase LC is going to account for about 75% of all HPLC applications that we see in the literature. And it's fair to ask why this would be, right? There's nothing inherent about this that seems like it should work so much better than all the other modes we've talked about, or be more universal. So why does it eat up so much of the literature space? There's a couple reasons. The first is that aqueous mobile phases are just good. They're just awesome because they're inexpensive, right? They are non-toxic. And they tend to be highly compatible. And by highly compatible, I mean with most analytes, with most detectors, even with most stationary phase support materials. So we've talked in the past about polymeric support materials swelling with organic solvents, and that's a thing, right? So so this is nice too, to not have to worry about that when most of your mobile phase is aqueous. Yeah, aqueous. There we go. I spelled that okay. I hope. Okay, and the other thing is that the stationary phase, because we're relying on when you think about nonpolar things dissolving other nonpolar things, we're talking about things like London dispersion forces, right? We're talking about hydrophobic effect. And so our stationary phase is basically exhibiting an overall weaker or lower degree of binding forces. Right? So, I mean, I think we can all agree that London dispersion forces are lower energy interactions. They are weaker binding forces than, say, the hydrogen bonding of an OH group. And this comes back to that thing that we've said is bad about adsorption all along, and that is that reduced retention factors, these are going to mean faster analysis. So faster analysis, not just faster, but better, right? Because the faster this analysis, the less band broadening we see due to things like longitudinal diffusion. We're also going to see improved, that's not a B, that's a D, everybody. Improved mass transfer properties. If the stationary phase doesn't hold on to this stuff as strongly because the forces involved are weaker, then we're going to have faster kinetics into and out of that stationary phase. And that is going to give better peak efficiency. To remind you what that means increased number of theoretical plates. All right, that's what we're going to say about reverse phase LC. One more topic for the day. It's not going to take too much time. We are going to move on to one more video about hydrophobic interaction LC, or HILIC.